So next up, we have Gabriel Konar-Steenberg, who will present on PowerAnalytics.jl, User-Centric Power Systems Analysis in Julia. Gabriel is a researcher at the National Renewable Energy Lab. So the stage is yours.
There we go. Okay, I'm Gabriel Konar-Steenberg. I'm a researcher at the National Renewable Energy Lab. One of my main projects there is this power grid modeling platform called Sienna, and I'm here to present on a simulation output analytics suite I designed for that platform called PowerAnalytics.jl. So first I'm going to give a brief introduction to what Sienna is, what it can do. I'll identify, I think, the gap that I found in Sienna that Power Analytics aims to fill and what the users need out of an output analytics package in this ecosystem. I'll then go into depth in terms of the design of the Power Analytics package. I'll then kind of abstract away a little bit and talk about the design principles and techniques I used to design this package. I'll talk about how it's being used right now, its status, and what I'd like to do in the future. And then I'll try to synthesize some takeaways for package designers. So first of all, what Sienna is. It's this open source ecosystem for power system modeling. So it's a collection of open source Julia packages that we like to split into these three applications. So there's Sienna Data, which is a bunch of data structures for modeling a power system, all the transmission lines, the buses, the generators, the loads, that kind of thing. And time series that can be used to drive these components, that kind of thing. Various input data parsers from industry standard formats and some exporters to similar formats. And we've got a library of test systems, all of that. The Sienna Operations, Sienna Ops application. This is where most of the simulation happens that I'll be talking about today. So you can kind of think of this as like a compiler or an interpreter from this domain-specific power systems modeling language to a sequence of jump optimization models that go out and call a solver and then return the results, and then the data flow gets managed as well. So this can be things like unit commitment, which is the problem of given some load you want to satisfy, how do you turn your power plants on and off to meet that load in a least cost way. Economic dispatch, so once you've committed units, what levels to drive them at to meet that load, again, in a least cost way, that kind of thing. And we can run various other simulations, but basically in the end, we have this HDF5 data set, very heterogeneous, very big, of the simulation output, and we need a way to analyze that. So that's what I'm going to be talking about today. We also have this third application, Sienna Dynamics, which is less relevant today. So at a very high level, very bare bones schematic, this is what a power simulation might look like. So we've got our package imports. We're going to load one of these test systems. You could also build your own system, of course. We're going to just modify one of the batteries in there, make things a little more interesting. And then we need to map components in this system to how they're going to be modeled in terms of the formulation for the optimization problem. So we do that with this template. We're gonna load a standard one, and then we're gonna set a specific model we want to use for that battery. Sienna has the ability to run multiple problems in a single simulation. So you could run a unit commitment and an economic dispatch and have them kind of chain together, and it would manage that information flow. Here we're just going to do a single model. So you set all that up, tell it how much to run, and then when you build it, it'll initialize this jump model, and then it'll run the thing. So once you've done this, you've got a big, like I said, heterogeneous HDF5 file with all the results for the variables and the parameters. There's a few ways you might think about to analyze this. You could use a third-party tool like SQL or anything you might find in Python or whatever. We really aim with Sienna to be friendly to users who are not sophisticated software developers. For many of them, learning Julia itself was already a pretty heavy lift. And so we really want to keep the additional languages to a minimum. So this is a Julia native solution. You could think of people writing their own analytics from scratch. We expose a data frames interface, so it could just be data frames manipulation, but this tends to involve a lot of duplication of work. There's a lot of common quantities that you might want to calculate that it makes no sense for people to all calculate themselves. It's also pretty bug prone and leads to pretty long, convoluted analytics scripts. Before this 1.0 release, we had an old version of Power Analytics that had a few hard-coded sets of calculations, but it wasn't quite fully featured like we wanted it to. It could do like curtailment, but not integration. It could do certain aggregations, but not others. So we wanted something more modular and fully featured. So that's what I'll be aiming to design, what I aimed to design and what I'll be presenting here. So we can kind of think of this package as having 3 main parts to the workflow. First, you're going to select your components using a component selector. Then you're going to compute metrics on those components, and then you can do some post-processing on the output of that. So here's those 3 parts again. The component selector lets you flexibly express what part of the power system you're going to be analyzing for a given query. This could be something like all solar plants in one group and separately all wind plants in another group. It could be something like all solar plants in the system, but only if they're larger than 15 megawatts rating, and we want them all to be grouped individually. It could be something like all loads in a particular geographic zone all clumped together, that kind of thing. And then a metric specifies what results you want to work with. It can specify arbitrary Julia code for computing secondary quantities from those results, and then it also knows how to aggregate itself across space and time. So this could be as simple as just looking up the power variable from the optimization problem results and summing up across everything, or it could be more complicated, like integration. This is where you want to measure what fraction of load was met with a particular flavor of generation, and that involves some more math, and maybe you want to sum that across those generators and average it across time, that kind of thing. And then that's going to output a dataframes.jl data frame, and then we embed a bunch of metadata in there so you can do post hoc further aggregation and plotting and that kind of thing on top of that. So now I'll go over each of those parts in greater detail. So precisely, a component selector is a lazy, partitioned, named, source-independent collection of components. I'll go over what that means. So at its most basic, here on the first line, you can see we're making a selector from this type, this abstract type, renewable gen. That's just going to capture all the renewable generators in our PowerSystems.jl system. So you can see we can call get components with that selector on a system. It returns this iterator of components. You can see if we've got a slightly different system, we can use the same selector to get what that applies to in that system. So this can be useful for like multi-scenario analytics where you've got a bunch of slightly different systems with slightly different simulations, and you can use the same component selector for each. We can also see that this is grouped. So the default is to group each component individually. So you can see if we call get groups on that selector as applied to the system, we get a vector of all the groups, and it's just all the individual components. But that's configurable. So now we're going to make a selector from all the generators, but this time we're not going to group individually. We're going to specify this partition function, get prime mover type. And this is a Power Systems function that can be applied to a generator to return its prime mover. And you can see that if we just call get components, it's that same iterator again. But if we call get groups, you can see that they're separated into various types of natural gas generation. We've got some hydroelectric generation in there, some wind, some PV, that kind of thing. And then those groups are themselves component selectors. So if you get one of those groups, you can call get components on it, and you can see that it returns a subset of the get components of the top level selector. All right, more component selector stuff. So here we're specifying a filter function to further specify what we want to include at all in our selector. So here we're saying we want only the generators with rating above 15 megawatts and only those with a prime mover type of photovoltaic. And we're going to give that a name. Then we're going to do a simpler selector, just all the thermal standard generators, and we're going to give that a name. And then we can compose a selector from these sub-selectors. And when you do this, the groups come from the sub-selectors. So you can see cell 5 here has the 2 groups corresponding to its constituent selectors. Component Selector was designed for Power Analytics, but it's actually available across the Sienna ecosystem now in case you might have use cases for this kind of functionality elsewhere. All right, moving on to metrics. So again, metrics are things that you can either look up from the results or calculate from the results that know how to aggregate themselves. And typically, these are per component selector. We provide a bunch of built-in metrics. So you can see we've got the ability to calculate the active power, we can do curtailment, we can do integration, we can do total cost, and then I'll show you later there is ways to construct your own metrics as well. So here we're going to take the calc active power metric. This is an instance of a struct, but it's callable like a function. So you put it there, you put the component selector there, and you give it some results, and it'll calculate the thing. So here it's just looking up the active power variable from the optimization problem, and then it's aggregating according to the groups in that component selector. So here it's summing up according to all the prime movers. That's configurable, of course. So you can see we're looking up that the component aggregation function for this metric is sum, but we could make a new metric built from that old metric except changing that aggregation function to mean. And you can see that we get a table of the same shape, but now it's averaging across the generators in each of the groups rather than adding. Here's how you can define new metrics. So this really shows that we can run arbitrary Julia code here. It's not limited to just looking up results. We've got this function here that takes a results set and a component, and it'll look at the time series of results for that component and compare the battery output power variable to some arbitrary threshold. So this is just going to give true if it's charging faster than a certain threshold and false otherwise. You can see then that we bundle that into a metric, and then we call it just like the metric on the previous slide, except on this selector composed of the only battery that happens to exist in my system, and it'll return this data frame with the results of our custom metric. So very extensible. The dataframes.jl data frames that the metrics output have a ton of metadata embedded in them, which lets you do some neat post-metric aggregation and plotting. So here on the first line, we're getting a big long data frame of all the active power across all 755 time steps in our month-long simulation. But then we can aggregate that time down. By default, it just aggregates down all the time into a single row. And this is done with the aggregation function specified by the metric and embedded in this table's metadata, dataframes.jl metadata. You can specify different time aggregation to that aggregate time function. So here at the bottom, we're specifying day of week. So then that first row is going to be all the generation that occurred on Monday. The second is all the generation that occurred on Tuesday, etc. Another thing you can do with data frames metadata is some nice plotting. So this is mostly just to show that this is doable, and I'll talk about later how we intend to have a more user-friendly interface to this plotting functionality. But here you can see that we're getting that data frame, and then we're looking up in the metadata how many components were aggregated together to form each column. So we can add that to our legend here. So we've got this nice hourly plot aggregated by hour of day of the various types of renewable generation that's occurring in our system. You need not try to read all this, but this is just to say that there's a bunch of other features. We've got some easy results loading routines that work for multiple scenarios. We've got computation of multiple metrics at a time and putting them in a nice little summary table. So I'd encourage you to check out our tutorial online. I've got a QR code at the end of the presentation. So that's the package. I'd then like to take a step back and talk a little bit about how I designed this package, what design principles are at play. And I think the primary one is that we really need this to be a simple, fully featured, user-centered interface. And that is enabled with Julia language features. So in terms of the user-centered design, first thing I did was took one of those existing, very manual analytics scripts in Julia, and I was like, how can I simplify this? So in the end, I was able to reduce the number of lines of code in that script by 2/3, from almost 300 to just about 100. and it does the same thing. At the same time, I've really had a focus on ruthlessly eliminating complexity from this. So software designers have asked me again, why not SQL? Why not something? Why reinvent the wheel? Again, our users don't know SQL. Our users sometimes just learn Julia just to be able to use Sienna. So it's really important that there be a solution in this kind of Sienna design language that they took the trouble of learning that works just for them and is designed to be simple just for them. That said, there is kind of an isomorphism with SQL that I'll show later in terms of the fully featuredness of this. Why not a custom tables.jl type to do all that custom metadata stuff? I have considered this, and we might be moving to this in a future design, but for now, people are already familiar with dataframes.jl, and even the slight changes to a like similar interface but a different type seems like unnecessary confusion for the moment if we can make an existing thing that the users are exactly familiar with work. In terms of performance and power, component selector, as you saw, very extensible. You can even define your own subtypes of that abstract type if you want to. It's all transparent to the user. They just need to know about component selector and make selector. Metrics, we saw that you can make your own metrics with the existing types, and you can also subtype metric if you need a different way of computing these under the hood. In terms of performance, we've got this big data set, big simulation of the entire eastern interconnection of the United States, so this giant grid with hundreds of thousands of buses and thousands of generators. I'm running 3 analytics across various, still thousands of generators, subsets of those generators, and the whole thing takes about 1.4 seconds after compilation. So pretty good performance on the largest grid we have. And then on the next slide, I'm going to show that the isomorphism with SQL to do fully featured analytics is there. And in fact, we provide a little bit more power than SQL. So here I've given a table where I've manually computed the component groupings and the component filter function and the timestamp grouping, which PowerAnalytics does for us behind the scenes. And if we had a table that looked like this in an unpivoted format, then the big long nested SQL query there at the top is roughly equivalent to the general PowerAnalytics call on the bottom. Julia language features used to design this, lots of functional stuff. So the functor pattern in terms of callable metrics. Metrics in general are pretty functional. So you can see here we've even got this function compose metrics that takes multiple input metrics and a reduction function and creates a new metric that's like the function composition of the constituent metrics, and this is used to define some of our built-in metrics, and users can use this as well. Lots of multiple dispatch, of course, behind the scenes. That's how the component selector extensibility is working. There's lots of subtypes of that under the hood, but the user completely doesn't need to know about any of that. That's how the metric computation works under the hood as well. And of course, the compilation for performance, being able to run arbitrary code in each of these analytics and have it be fast due to compilation. Right now, this is being used at NREL for a few regional studies. I've got a map here of the regional technical assistance projects that we're currently planning and are likely to use PowerAnalytics in. We're also using this for some extreme events research, and this is a published package, open source 1.0, ready for the community to use as well. Things I'd like to do in the future. I'd like to make the component selector composability a little more fully featured. I'd like to support set operations like set union and set intersection. I'd like to make it a little easier for users to create their own metrics. We've got some performance work to do, I think, some type stability issues that lead to longer compilation times than I'd like. And then maybe one of the biggest ones, I'd like to give the same makeover to our Power Graphics package, which is meant to support plotting in the Sienna design language. And then I've just briefly got some takeaways for package designers. This was my first Julia package design experience, and I learned some things from it. So first of all, I think it worked really well for me to meet my users where they were and ruthlessly focus on simplifying the syntax, simplifying how they need to interact with this package to make it very easy to use. And then I think it worked well for me to work in terms of this theory of abstractions. So I've got the component selectors and I've got the metrics, and those are like objects with a theory of what they do, rather than this kind of collage of features. Things are kind of grouped into those intuitive abstractions, and that really helps, I think, conceptualize the package. And then finally, of course, you should have fully featured documentation that describes in detail how everything works. But at the very least, you should seek to communicate to your users what the package can and can't do, so everyone's on the same page about that and the expectations are managed. I'd like to acknowledge a bunch of my coworkers here. First and foremost, Sarab, who kind of first started this project and secured a bunch of funding for it. A bunch of people helped with design and code review. Akrivi wrote that tutorial that I had a screenshot of. Lots of collaborators here. Here's a QR code to check out the documentation website. It's got a bunch of reference there. It's got the tutorial I mentioned. It's got a link to our GitHub, that kind of thing. And I'd be happy to take any questions.
We have some time for questions if there are any. If not, you can always. Yeah, okay.
When you refer to simulations, how do you perform simulations? Is that because you get data from something else and you extrapolate, or what exactly do you mean by that? Yeah,
so simulations are like, we have a system with like a time series of load. So like this is the load that we need to meet, and we're simulating how to turn the generators on and off to meet that load, that kind of thing.
Is it because you want to, I don't know, supply some kind of level of capacity for, I don't know, a specific, I don't know, city or, I don't know, something like that?
Yeah. Basically, the way that particular problem works is we want to exactly meet the load, no more, no less, respecting the constraints of the power grid, and doing so in a least cost manner.
And I assume the simulations take into account, I don't know, different features in your, I don't know, plant or factory or whatever you call it, I don't know.
Yeah, for sure. So we take, this is very configurable, and there's no one simulation. It's kind of whatever you wanna do. But yeah, we can take into account features of the power grid, features of how the generators themselves work, all sorts of things. I've been developing separately from this the ability to dispatch against market bid prices, so like time variable prices that compete in a power market, that kind of thing.
Any more questions? Okay, give me a second.
Hi, thanks. It's interesting to see a discussion on power system and analytics here. I don't see much discussion on, let's say, the shadow prices on, or just dual variables of the constraints or the simulation model. So I'm wondering if that's part of the analytics where the metrics that users are defining, or is it a feature?
Yeah.
Request?
So the simulation certainly outputs those duals, and so they're there for metrics to grab. I believe our total cost metric does grab a dual, and in general you can certainly define metrics that key onto duals.
Cool, thanks.
Any more questions? If not, you can always find our speaker during the lunch and ask him many more questions. So
I've got stickers, and I've got a completely different presentation later today, if anyone's interested.
All right, let's thank the speaker again.